couple more examples of using the logistic model for those of us that need a little bit more. So in this example, we're told that the population of Alaska from 1900 to 2000 can be modeled by the equation P of T equals that thing, where P is the population and T is the time in years since 1900. So that fits the logistic model, the solved model. So we probably want to pull out some numbers from here, right? So since this is logistic, that is not a highlighter, right? Our L value, our limiting factor, is 895,598. And then we know to find the K, if we need to find that, this exponent here, change colors, right, negative 0.0516 is equal to negative L times K. So I can take out the negatives there, and then I know what L is, so I'm going to go over to my calculator and do 895,598, nice little palindrome there, divided by I have it the other way around. Whoops, clear that. Right, it should be that K value, that number right there, 0.0516 divided by L, which is 895,598. Double check that I typed that in right. Yep. And we get that number. So I'm going to write that down, right? So K equals 5.762 times 10 to the negative 8th, but I'm going to store that as K on my calculator, so that way I don't have to type it in every time. So I'm going to hit the store button, alpha, and then I'm going to find my K, which is above my opening parenthesis. I'm actually just going to go ahead and store my limiting value as L as well, so that way I don't have to type it in every single time because I'm lazy. And there we go. Okay, so going back over to this, we want to know what is the predicted population of Alaska in 2021, so this year, right? So if we know, right, T is the time in years since 1900. So that's going to be T equals 121. So I'm just going to plug that into my equation. So I get P of 121 is going to equal my L value, right, over 1 plus 71.57 e to the negative 0.516 times 121. So I'm going to go over to my calculator. I'm going to set up a fraction by going alpha y equals. I don't want to type that number in again, so I'm going to hit alpha L, so it pulls that up. And then I have 1 plus 71.57 times e raised to the negative 0.0516. Just realized I forgot that 0 when I wrote it down. Move the decimal point there. There we go. Times 121. So my predicted population is 786,267.725, right? And that doesn't make sense to have 0.725 of a person, so I'm just going to round that up. So that's going to be approximately 786,268 people, right? 786,286 people. Okay. So how fast is the population changing in 1940 and 1999? So we know our L value is 895,598, and we found our K, right? We know that K is, writing it down again, 5.762 times 10 to the negative 8th. So if we want to find how fast the population is changing, we really want to know, right, we're trying to find the rate of change of the population in terms of time, so dp dt. So we need to know the derivative. Now, of course, you have the model, so you could take the derivative. You can also do a numeric derivative on your calculator, so I'll do both ways just to kind of show you how to do that. But we can find the model really easily, right? So we know that the logistic model follows that dp dt, right, just making sure I get this right, should be equal times K times our quantity, which in this case is P, times the limiting factor minus the quantity. Again, that's P. So we know what those are. So I have those values stored in my calculator, but if you want to write it out, right, we have 5.762 times 10 to the negative 8th. Now you probably see why I stored that, right, times 895, 598 minus p. So we need to know the p-values in order to find these quantities. So I'm actually going to go back over to my calculator, and I'm going to, you know what, I'm going to go in and put that function into my y equals screen because that might be easier for me. So again, I don't want to type in that number again, so alpha L, since I have it stored, 1 plus 71.57 times e raised to the negative 0.0516 times t. In this case, we'll make that an x. So go back to my home screen. So say I want to find y1, so I'm going to go to alpha trace, and I want to plug in for 1940. That's going to give me a t value of 40, right, because it's years after 1900. So I'm going to type in 40 here. So I'm going to get that p of 40, and you guys can't see this because I'm writing it down on the iPad, which is behind it, right? P of 40 is equal to 888,000.8548. So then I want to find my dp dt, right, when at p of 40, so that is t of 40. So I want k times p of 40 times the group of my L minus p of 40. So I'm going to actually just type that in. So I have alpha k times my answer. So I'm going to actually use second ANS here for answer. And then I want to do my limit, so alpha L minus that number I just found. So my rate of change here is approximately 4,127.795 people per year. So we're growing at a pretty large rate per year, adding another about 4,128 people per year. So now if I want to check, I can also do a numeric derivative on my calculator. If we go to alpha, I believe it's window, yep, alpha window or the math menu, right, you can go down to numeric derivative. I want to take the derivative with respect to x. I have my function stored in y1. So you can go to the vars key to do that or hit the alpha trace key as the shortcut, and I want to plug in 40. See, I get the same exact number, right? The rounding at the end is a little different. So why don't we do this now? Going back over to the iPad. Apparently I ran out of room, so I'll make that a little smaller. Right, so now if I want to find well, that was awkward. The iPad just disappeared. If I want to find, oh, pull that back up. Now you get to watch me join Zoom. Okay. Love technology. And there we go. Right, nothing happened. Okay. Get rid of that. Okay, so now if I want to find dp dt for when t is equal to 99, right, that's 1999 there. Right, I'm just going to use that numeric derivative method because it's probably a little faster. Just wanted to show you both ways. All I'm going to do is copy down that line, change my t value to 99. So we are now increasing at 9,741.748 people per year. Right, so those would be our answers. Right, the numeric derivative way is probably a lot easier, especially because you'd have to have a calculator to do this. Okay, one last example. Oh, we're just actually going to keep going with Alaska here. Forgot about that. So we want to know what is the population when it is growing the fastest. So the population is going to grow the fastest at L over 2. Right, so that's going to be 895,598 divided by 2. So on my calculator, I'm going to type in alpha L divided by 2. And that's going to give me 44,799 people. Right, so if I wanted to give a nice complete answer, since it asked what is the population when it's growing the fastest, right, we might say as a sentence answer, the population is growing the fastest when the population is 447,799 people. Right? And so the final question about Alaska for today is, what does this information tell you about the long-term population of Alaska? Right? So what they're really asking is, what is the limit as t goes to infinity of p of t? Well, that's always going to equal the limiting factor, which in our case is 895,598. Right, so that means that over time, right, that is what the population of Alaska is approaching. So I'm going to do one last quick short example. I want to talk about some bears. Right, so we have the growth of a population P of bears in a newly established wildlife preserve can be modeled by dp dt equals 0.008 p times 100 minus p. So, right, so that's a logistic equation right there. Right, that fits the form. So that tells me that my L is 100 and my K is 0.008. So we want to know, what is the carrying capacity of the wildlife preserve? Okay, so that's the limiting factor. So the carrying capacity is 100 bears. What is the bear population when the population is growing the fastest? Well, that's always L over 2, so 100 over 2 is 50 bears. Right? Again, you could write out a nice sentence answer that says the population of bears is growing the fastest when there are 50 bears in the wildlife preserve. Right? And what is the rate of change of the population when it is growing the fastest? So in other words, what is dp dt when p equals 50? Right? So we're just going to plug 50 into our model. Right? So hopefully you guys wrote it down. I'm going to scroll back up. So 0.008 times 50 times 100 minus 50. So 100 minus 50 is 50 as well. So I'm really going to do 0.008 times 50 squared. And that's going to give me 20. So since this is a word problem, we do want to put some context in it. So it is increasing at 20 bears per year at that point.